This is geochronology, as opposed to the last talk. Going to shift gears here a little and talk about geochronology as opposed to geochemistry. The main message of the talk is that there's been a quantum leap forward in argon mass spectrometers, which I think offers a lot of advantages in dating tephra. The outline of the talk is first I'll speak a little bit about the dating of tephra, talk about the new mass spectrometers, give you a few case studies, and then just briefly consider some outstanding problems. So for dating the tephra, any eruption, at least that's intact, you can date it at the source volcano, either ignimbrite or proximal tephra, or you can work further out on the tephra sheet. To use the argon 4039 method, you need K-bearing phases. As Ryan just said, K feldspars, sanidines, or anorthoclase are the best materials to work with. You can also date hornblende, biotite, plagioclase, in some cases glass. For this talk, I'm going to concentrate on the K feldspars. The argon-argon method depends on the decay of potassium to argon-40, half-life of 1.25 billion years, so it's useful for anything from the 4.5 billion year age of the Earth on down to, in some cases, the Holocene. In conventional KAR, you measure the ratio of you measure potassium in one sample and argon in the other. But for the 4039 method, depends on neutron irradiation. So you dose the samples with neutrons, convert some of the potassium to argon 39, and the ratio of argon 40 to 39 is proportional to the age. The gas has to be extracted from the sample by heating, melting, or ablation. In most cases these days, we use lasers for that. And then finally, the analysis is made with a mass spectrometer. Really, for tephra dating, you're far, far better off using single particle techniques, as a lot of the geochemical methods today have said, just because of grain-to-grain variations, possibility of xenocrysts, etc. And what the single crystal method allows you to do is to distinguish xenocrysts from the juvenile material. There's an example over on the right, one set of juvenile crystals at 295,000 years, a couple xenocrysts at much older ages. Now, depending upon your instrumentation, your single crystal dating is limited by grain size. And so typically, you can almost always use single crystal techniques at the source volcano, dating ignimbrites. As you get out onto the tephra sheet in the proximal areas, you can use single crystal dating. Eventually, when the crystals get small enough, you have to resort to multi-crystal dating. And as you get even further out on the sheet, then into the distal areas where you get very, very small or no potassium feldspar crystals, then you have to rely on geochemical correlation. Up until just a few years ago, virtually all the dating that was done on tephra was done with MAP machines. MAP, mass analyzer products, mass spectrometers came out in the late 80s and have been kind of state-of-the-art ever since. Up till the MAP came out, every 10 years or so, mass spectrometers, argon mass spectrometers would get about 10 times better every 10 years. But that didn't happen after the MAP, and it wasn't until just a few years ago that new generation machines did come out that are, in fact, 10 times better. These are three of the new multi-collector machines that are out on the market. Two from Thermo, one from New. One of the The major differences between these and the Argus is that they're all multi-collector. In the case of the Argus, we've got 5 Faraday collectors and a multiplier, and then other combinations in the other machines. Other advantages are improvements in detector technology, particularly very quiet ion counters and very low backgrounds. Our lab has got 2 Thermo Argus 6s that we commissioned a couple of years ago. The advantage of the Thermo Argus 6 over these other machines is the very low volume, about 600 cc's, which gives it a very high sensitivity, so we can work with very small crystals. A pleasant surprise on the Thermo Argus 6 was really how low the backgrounds are. And our argon 36 background is down at about 1 count per second, 2 orders of magnitude less than our MAP. The drawback with the Thermo Argus 6 is it's a low resolution machine, but that so far has not proved to be a drawback in working with Tephra. So the precision in terms of just measurements of isotopic ratios in the MAP was at best about 1 part per mil, a 1/10%, and in practice sometimes pushing closer to 1%. The new generation machines drop that by an order of magnitude, so we're now measuring in the worst case at about 1/10% and pushing 2 or even 1/100%. So the good news is we've got this fantastically improved precision. The perhaps bad news, or at least slightly vexing news at first, is that this high precision allowed us to identify quite a number of problems that before we were lost in the noise. And these include irradiation artifacts, extraction artifacts, some issues about the accuracy of the isotopic measurements, and then we're getting a better handle on some of the sources of geologic error. The problem became apparent when we compared measurements of gas samples with measurements of geologic samples. Most argon systems have gas bottles on them, shown by these bottle figures here, where we use as standards. In the case of our lab, we've got a bottle of atmospheric argon and plus a synthetic standard that has argon 39 added, which is an analog for Fish Canyon Tough, one of our main standards. And when we measure this synthetic standard, and if we calculate it as if it's a real geological material, the uncertainties on the measurements are on the order of 5,000 years in 28 million years. And if you look at the array of several measurements, they form a nice unimodal distribution on a probability diagram with an MSWD, which is low enough to suggest that the analytical error explains most of the scatter in the data. In our earliest measurements of geologic materials, what we saw, this black is data from an MAP, from actual crystals of Fish Canyon Sanity in one of our standards. We saw a nice unimodal distribution, but when we first started making measurements with the Argus, what we found was this very spiky distribution and very high MSWD, suggesting that there is much more variation than can be accounted for by analytical uncertainty. Well, much of this turned out to be related to an irradiation artifact, which was we irradiate the samples in small aluminum discs with wells on the order of 2 to 6 millimeters in diameter. And once we were able to use the new machines to map that flux distribution, we found that there was much more variation in flux across those irradiation pits than we had formerly thought. That problem was relatively easily solved by going to smaller irradiation pits, typically 1 millimeter, which reduced the spread in flux to something similar to our analytical error. Another problem that we recognized once the precision was a little better was that most or all sanidines don't have flat age spectra. These are incremental heating diagrams where we're taking single crystals, heating them stepwise, measuring the ages, and then looking at the data on this plot, argon released versus age. And every sanidine now that we measure age spectra on show this climbing spectrum. And this, the cause for this is in the literature. There's a paper by the ANU group on this, where they consider many different causes for this. Some think it's a recording of magma chamber history. Some think that these are defrosted grains that have been degassed, or possibly a recoil artifact. We think, in fact, this is an artifact of extraction caused by faster diffusion of the argon-39 than the argon-40. One of the main pieces of evidence for this is that the scale of this, the scale of the non-flatness of these spectra scales as a percent, typically about 0.5% of the age in all feldspars, which makes us think that this is something experimental, like this extraction artifact, rather than something geological. Otherwise, this effect would be larger in young materials than old. But the effect of this is that if you don't, we get much better agreement with the total gas age, the integrated amount of all these steps, than we do from portions of these spectra. So if crystals are incompletely fused, they'll have a slightly younger age. If they're preheated, which is a common practice in argon geochronology, they might have a slightly older age. And we think that this is also a cause of part of the scatter that we're seeing now that we have the higher precision. We also think that part of the scatter is in fact geologic. And one of the features that you see in certain tuffs and certain rhyolites is this tail of older ages. And this is some data from Ellis et al., 2012, Huckleberry Ridge Tuff, where there's pretty tight group of ages. This is MAP data, and then this tail going off to older ages. And this has been explained by many workers, Ellis and others, as a consequence of degassed xenocrysts. Other people think that maybe you're looking at extended time in the magma chamber, or that it's an excess argon 40 problem. We're pretty convinced now from work on this unit and other Yellowstone units that this is a consequence of excess argon and melt inclusions. And I stress that this is not a problem in all sanidines. It mainly seems to be in tuffs from intraplate volcanoes, and you see it's very pronounced in most of the Yellowstone units and Mount Erebus in Antarctica. Here's an experiment that helped convince us that this is a melt inclusion problem. This is out of a younger Yellowstone post-caldera unit, and we see this in many of the young Yellowstone units, where if we date complete phenocrysts with any amount of melt inclusions in them, we see this scatter of ages, in this case all the way from 160,000 out to 300,000. If we take the same phenocrysts, grind them up, remove the melt inclusions with HF, we get a very tight distribution of ages, which we believe to be an accurate eruption age. So what the new mass spectrometers have effectively done is to move these boundaries out further on the tephra sheet. Now we can take single crystal dating much further out on a tephra sheet than we used to be able to. We can take multi-crystal dating out to further, out closer to distal parts of the tephra sheet. And still, if we have no phenocrysts, we're still use geochemical correlation to get the age, but we're able to do more with the argon dating. So I'll give you a few examples of results from the Argus 6, starting from a source ignimbrite, moving out to the distal end of the tephra, and then and also an example about how we think you can do more with heavily reworked tephra than we used to be able to. Example here from a source ignimbrite in Ethiopia. 5 different samples of the ignimbrite, fairly large crystals in this case, 800 microns. And here's ages from the from probability distributions of ages from the different samples. And these ages range from 294 to 296 Ka, errors on the order of 1 to 2 Ka, much better than we could have done with the MAP. This is a relatively proximal tephra. This is actually just same unit Brian talked about, the IRZ coal near the KT boundary in Montana. This is data, MAP data, analytical error on each measurement and the overall spread. You can see there's 1.2 million years roughly from the youngest to the oldest analysis, whereas data from the Argus, much smaller analytical errors on the individual crystals. And then the spread of the whole data is similar to the analytical error on one crystal from the MAP. So much more precise data, relatively good agreement here with uranium lead zircon age from MIT. Here's moving out right into a much more distal tephra. This is an Antarctic tephra, not one of the ones Neil talked about in West Antarctica, but it's an East Antarctic tephra collected near Allen Hills. Very small crystals, up to 100 microns long, but little needly anorthoclases, 20 microns across. Back when we analyzed these with the MAP, we were analyzing hundreds to as many as roughly 1,000 crystals, and we saw quite a wide range of ages, ranging from these 4 to 6 million years, some even older, some a little younger, but we could just not get any kind of consistency with these bulk samples. Obviously, a problem with contamination. With the new machines, we can't quite get down to the single crystal level, but we are able to do 2 crystal fusions, and this is, in fact, work done by Nels Iverson here. And what we found is we're able to identify 5 crystal fusions that have very old contaminants in them, and have identified a population here at 220 plus or minus 50, and we're working on revising or on improving that measurement. So lastly, I'd just like to talk about rework tufts, and there's been quite a bit of discussion of rework tufts today, and how there's certain amount of reworking in many tephra that tephra chronologists work on. In some cases, this is very extreme reworking, where you're really looking at a sandstone or a siltstone with very, very small amounts of the initial tephra. In this case, this is data from near the KT boundary in the San Juan Basin of New Mexico, and we perhaps one crystal out of 1,000 out of 1,000 grains of feldspar is a good-looking volcanic sanidine. There's lots of plutonic K feldspars as well. These are these dark grains. So we picked large numbers of these sanidines from these tephra, and these are pretty small grains, 100 microns to maybe 200 microns. And in these volcanic crystals from this tephra, we find a population of older, or a group of older feldspars, 70 to 80 million years, reworked from 10 million years of different tephra layers, and then a population here at 65 and a half that we think represents a very good maximum depositional age, a little less useful than a depositional age, but still useful. And in some cases, these may approximate depositional ages. When we look at a sequence of these units, and this is vertical stack in stratigraphic order, work mostly by Ian Mason and Matt Heisler. We know that the K Paleogene boundary is here, although it's an unconformity. There's probably a fair amount of material missing. And none of these are really, strictly speaking, tephra. They're all tephra-bearing sandstones. And in some cases, in many cases, we see, again, these populations of crystals going from, in the 70s, plus a population at an age that is close to 66 million years. Some of the samples don't give useful ages at all in terms of approximating the depositional age, but a number of these give ages that fall in stratigraphic order and in fact may approximate depositional ages. So there's probably more can be done with these highly reworked tephra than have been to date. So in conclusion, the new generation multi-collector mass spectrometers have improved precision greatly, and now we're working on accuracy. Precision's up by a factor of 10 or probably 20. This high precision has revealed a number of sources of error, some of which can be mitigated: radiation artifacts, extraction artifacts, and geologic errors. I think these new machines improve dating of proximal, distal, and reworked tephra, and we still have a number of outstanding problems that we're working on, but I won't discuss those in detail now. So thank you very much.